Okay, so thank you very much for the organizers for giving me the opportunity to talk here and for the wonderful workshop. Today I'm going to present like an interesting problem and some preliminary work me and my colleagues have done. This is joint work with Luis Ortega and my supervisors Aritz Perez and Andres Mascos. So let's first introduce some basic notation. We are going to make a Bayesian inference with a training data set in some subset of the Euclidean space, and we'll have a probabilistic model M, which defines a likelihood with parameters theta also in Euclidean space. After we apply the Bayesian rule and have our posterior, one of the most important magnitudes we use to evaluate it is the marginal likelihood, which is basically marginalizing out the parameters in the likelihood with the prior. And this more or less tells us how probable is it that our model generated the data we have been given. The interesting thing about marginal likelihood is that embodies Occam ratios principle. So the idea that if we don't have any prior preferences between different models, we have to choose the simplest one in face of the same empirical evidence. So this idea is very old, but in the modern setup was pioneered by the work of David McKay. And the idea is that we can do Bayesian and principal model selection, choosing the model with highest marginal likelihood. So this idea has been extended and scaled up for modern Bayesian inference, and in particular to Bayesian deep learning using some posterior approximation techniques. And in practice, this has been used for model selection using marginal likelihood as a proxy for generalization. So the graph you are seeing there is taken from this very nice paper from Alexander Immer and his colleagues, where they use a Laplace approximation to approximate the Bayesian posterior on neural networks. And they then compute the approximated marginal likelihood, and they show that marginal likelihood correlates very well with the test accuracy. So we can use it as a proxy for generalization to make model selection. But that is not the end of the story. There is also this very interesting paper by Sanare Lofty and her colleagues, where they show that, well, marginal likelihood is very sensitive to prior choice. And that's not something new, but the idea that we can simply use marginal likelihood as a proxy for generalization error is not that simple. And they show that depending on the prior precision of the precision of the prior, marginal likelihood is often uncorrelated or even negatively correlated with the generalization error. So how can we disentangle this puzzle? The answer that Lofty and her colleagues give is very interesting. Marginal likelihood and generalization are related, but there are subtle and important differences. Marginal likelihood is telling us how probable is that our model generated the data we saw. And when we talk about generalization, we are interested in the following question. Given our posterior, how probable is, or how well the posterior predicts new data, which wasn't used on training, drawn from the same distribution. So marginal likelihood and generalization don't answer the same question. And we should be careful when using marginal likelihood as a proxy for generalization. So how does this happen? First of all, as I said, marginal likelihood embodies Occam ratios. And when we have a diffuse prior, like with high variance, it gives a lot of mass to alternative explanation. So marginal likelihood penalizes diffuse priors. Also, and this is even more common nowadays, when we talk about model selections, practitioners usually refer to prediction, to a generalization error, not inference, or taking the most likely model. And also, and this is very related to the general idea of this workshop of generalized posteriors, when we choose a prior in Bayesian machine learning, and more specifically in Bayesian deep learning, we choose it for computational conveniences. It doesn't encode the information we have about reality or about the data. So if we only care about prediction, marginal likelihood might not be the best choice. So given this, a natural question is to say, well, what do our theories of generalization, and more concretely PAC-based theory, say about the relation between generalization error and marginal likelihood? Here you can see one of the most important and basic PAC-based bounds, from which many state-of-the-art PAC-based bounds are deduced. This is work from Alquier, Ridgway, and Chopin. And as you can see, the two terms in the bound that are related to the posterior are the data fit error, the empirical risk, and the KL divergence. And when the posterior we are working with is the actual Bayesian posterior, and this has been pointed out in several talks before, so I don't have to delve very deeply into this. When we have the Bayesian posterior and our loss function is the negative log likelihood, we can recover the marginal likelihood in our bound. So essentially, and this is explicitly stated in Germain's paper, which was also mentioned, if we want to use PAC-based bounds to make model selection, meaning that we have several models and we select the model with smallest bound, we are essentially doing the same as model selection with marginal likelihood, because our bound will be monotonical with the negative log marginal likelihood. So maximizing marginal likelihood is the same as minimizing a PAC-based bounds. But this leaves us as we were in the beginning, because we have this experimental result saying that depending on the prior, and remember that the prior usually is only a computational tool, or we can also choose it for the regularization, but usually it's meaningless in terms of our expert information about data. So PAC-based bounds, or at least this kind of bounds, don't solve the problem of that sometimes marginal likelihood is not correlated with generalization error. So one straightforward thing we tried was to use a novel bound we introduced in last year New Reefs to try if we could still work this out in the framework of PAC-based bounds. The novelty of this bound is that the exponential moment term, in this case the cumulant generating function, is averaged by the posterior instead of the prior. So we have another trade-off parameter depending on the posterior that would weigh down the bound, even if the KL divergence is penalizing diffuse priors. I am not going to delve very deeply into the assumptions and everything, but if we do some proper assumptions on the data generating function, we can bound the cumulant generating function by a gradient term, and we obtain this bound where the KL divergence is multiplied by the expected input gradient norm. Input gradient norm, which is the norm of the loss with respect to the input data, is mentioned in adversarial robustness literature because it's often used as a regularizer. The idea behind that is that two data points which are very close should not have very different losses. So small input gradients mean that our model is somehow stable. So the natural next question is, how well does our bound predict the Bayesian model averaging loss? And here you have some preliminary results we have where we use very similar setup to Lofty and her colleagues. In the x-axis, you see the BMA test log likelihood, and in the y-axis, our input gradient PAC-based bound. As you can see, when the prior precision is big, that means the variance is very small, the correlation is very good, and deteriorates with when the precision is small, which is to be expected because of the KL penalizes diffuse prior. And this last graph is the correlation between the test log likelihood and the marginal likelihood. So even if it deteriorates with precision, it's still doing better than marginal likelihood. Of course, everything is not that good because we are making small tricks. For example, this input gradient norm is in expectation. So we are using test data to approximate it. So we are not being very fair to marginal likelihood because marginal likelihood is computed with empirical data. Also, we don't know this constant, which comes from the logs of Levy inequality we use to bound the moment generating function. So we used the grid and took the bound with the smallest bound. So this is somehow encouraging, but there are still setups where PAC-based bounds don't work if we only care about prediction and generalization error. And this has been developed by the literature on model misspecification. The idea is that PAC-based bounds and marginal likelihood target inference, recovering the best model, while when we do prediction in the Bayesian setup, we mostly care about the predictive posterior. So in this side, you see a standard PAC-based bound, which is bounding the expected log likelihood of a random sample taken from the posterior. And with a Jensen inequality, we see that this is always bigger than the risk of the predicted posterior. So there has been extensive literature on trying to directly bound this term, which is more directly related to prediction. And it is also known that when the model is misspecified, the smallest inferential risk and predictive risk, which this is the predictive risk and this is the inferential risk, don't have the same minimum, and there is a big gap between them. The main papers on this are that of Masegosa and Morningstar and his colleagues. This second one is very interesting. And we did a toy example to illustrate this case. We made a Bayesian linear regression with polynomial features. And in the x-axis here, you see the number of features we do. So for x equals 1, we only had a line. And the more we go to the right, the more polynomial degrees we use to fit data. The orange line here is the inferential risk. The blue one is the predictive risk. And the green one is the train error, just for reference. So you can see that the inferential risk is always bigger as predicted by this. This is just a Jensen inequality. And the interesting thing is that they don't have minimum at the same point. So when we do Bayesian model averaging, the minimum inferential risk is more or less when the model has 30 features, when we use polynomials of degree 30. But the inferential risk has a minimum in x equals 1. Why is this? Because in this case, we are fitting a high-frequency sinusoidal function with a few training data sets, so the posterior has a lot of uncertainty. So when we take a random sample from the model with 30 degrees, the uncertainty, we usually take a model that makes big mistakes where there is no training point. But if we allow us to do Bayesian model averaging, those errors cancel out and we fit data very well. So even if we had the tightest PAC-based bound in the world, it wouldn't allow us to find the best model for prediction, which is the one with 30 degrees. So there are interesting open problems if we want to do model selection in a Bayesian setup and target prediction, which is trying to have tools beyond marginal likelihood, possibly based on the literature on PAC-based bounds directly targeting the predictive risk. And the main idea is that this is very related to the general setup of generalized posteriors. And I am open for suggestions or ideas because this is very preliminary work. I hope you at least took an interesting problem home, and thank you for listening.
People have any? More a remark than a question. Thanks. It's super interesting. I love those papers. Both of them I think are really interesting. There is quite some work on doing this more for methodology. So without an associated guarantee. There are a couple of papers by Martin and co-authors doing this specifically with Gaussian processes with variational families that are also Gaussian. Because in that case, you can actually solve everything in closed, or like your variation objective is very elegant.
Yeah, your likelihood is closed form. Right?
Exactly, and they show this performs super well. The other thing, we were involved with something AI stats this year. The title is Prediction-Centric Uncertainty Quantification with Maximum Mean Discrepancy, which basically uses the maximum mean discrepancy to target the predicted directly as well. But we don't have PAC-Bayesian theory now, but it's sort of a methodological contribution in much the same way. So I think it's a really interesting question to study.
Thank you.
Well, I think in the interest of keeping on time, we're going to thank you again, and we're going to have a quick coffee break, then a final set of talks, and after that, a poster session. So please stick around for the poster session with loads of interesting stuff. Thank you very much.